Hi everybody, welcome back to Unit 8, AP Physics C, E&M. So this video is on electric flux. So we're still building upon this concept with electric fields. So now we're going to put something in there, right, into the field to see how it is affected, okay? So the way we think about it is flux describes the amount of a given quantity that passes through a given area. So it's like if you have water flowing through a pipe, the amount of water that flows through that cross-sectional area of the pipe will be the flux that goes through that area. Now, for an electric field that is constant across an area, the electric flux, the electric flux that goes through it is given by the equation. Oh, sorry, I was using my highlighter. Okay, phi sub E, because we will do a magnetic flux later, right, of E dot A, right? And so if you go to that calculus playlist, it'll talk about dot products. So this is a dot product. And so dot products are scalar products. So we're multiplying two vectors and getting a scalar in return. And so to simplify it further, it's just EA cosine theta. E is the amount of electric field. A is the area that is passing through, and cosine, the angle would be the angle that the area of it, has, if it's at an angle and so forth. So what happens is if I have an electric field, right, of magnitude E, and I have this area that it's passing through, okay, and you're looking at the area vector, which would be kind of like the face of the area that is passing through, not the fact that this is standing straight up and down, but it's like a window. So how much is going through the window? So the area vector actually is perpendicular to that window. So this would have the full, right, because they're at 0 degrees to each other. So it's just simply EA. Okay, so if E and A are parallel to each other, that's the maximum. Okay, and then what happens is your next scenario will be taking that area, right, and putting it at an angle. Okay, and then so your area vector would look something like this. Theta, theta is here, and so this would have a side of EA cosine theta. And then the last part would be, right, if my area essentially is laying flat in this electric field where the angle is 90 because your area vector points up. And so this would have a flux of 0 because nothing passes through it, right? So the direction of the area vector, again, defined perpendicular to the plane of the surface and outward from the closed surface. The sign of the flux is given by the dot product. So again, if they point in the same direction, it's 0 degrees, so that's going to be a positive flux. And if it points in the opposite direction, then it's going to be a negative flux. Okay. Now, what happens is the total electric flux passing through a surface is defined by a surface integral. Now, don't let that kind of scare you that now we're talking about surface integrals. The good thing about it is for AP Physics C, right, the answer is just going to be E times A. So here we have our integral. So it's the integral of E dot dA, right? And so it's the amount of passing through. But like I said, don't be scared because at this level, right, we're just looking at E times A, right? And so if we were looking at, kind of our examples, here's our squares, right, or rectangles. So then your area would just be, side squared if it was. So if we were looking at how much, how much flux is passing through there, you end up with like ES squared, okay? Again, they're going to want, this is typically a derive an expression question. Okay, so let's look at an example problem. So here we have a sphere of radius 2 centimeters, creates an electric field of strength 3 newtons per coulomb, distance 5 centimeters away. What is the electric flux through the surface of the sphere drawn at a distance of 5 centimeters? So one thing to note is that everything is measured from the center. So if we're looking at 5 centimeters away, this really doesn't necessarily play into the factor as much. But understanding that, because the flux is through the 5 centimeter circle or the sphere, right? So we need to derive an expression first for our magnetic flux, or excuse me, our electric flux. So again, don't let it freak you that it's going to be a surface integral. It's just E times A. But what you have to know is, what is the surface area of a sphere? And that's going to be 4 pi r squared. And so it's not a volume, right? It's the surface area. So now what we're going to do is we're going to plug that in, right? So we're going to say our flux is equal to E times 4 pi r squared. And now we just simply plug in. And so they tell us it has a strength in 3 newtons per coulomb. You got 4 pi. Our circle, or our sphere is 5 centimeters. Make sure you convert that to meters. And you plug it into your calculator. And so you have a 0.094 Newton times meter squared per coulomb magnetic flux, right? So that means that this is your unit for E, right? So Newton times meter squared, and then it's divided by C, right? So per coulomb. And I always like to write the subscript because coming up we're going to be doing magnetic flux as well. All right, so now we're going to wrap up the unit by talking about Gauss's law, which is an application, kind of putting it all together, okay, in this last topic.